Hey, everybody. Thanks so much for joining today. My name is Thaddeus Walsh. I'm a senior solution architect on the East Enterprise team for Elastic. I joined Elastic last September by way of an acquisition. So I was working as a solution architect for a small startup firm based out of Vancouver called CMD. And that organization was a security solution company, specifically around Linux endpoint security. So specifically using eBPF, or the extended Berkeley packet filter, which we're here to talk about today, to provide a new way of securing your Linux assets. That technology was very interesting to Elastic, so they acquired us. I absolutely love working for Elastic. It's an unbelievably fantastic company. And I get to do really cool and interesting things, talk to people about really complicated problems and any and every possible way that you could want to think about unstructured data. So what we're going to talk about today is eBPF, the basics. So let's get to the agenda. We've got a path. We're going to talk about the original problem that existed. We're going to talk about how BPF was introduced to solve that original problem. Then we're going to talk about a new problem and how a new solution to that problem, eBPF, or the extended Berkeley packet filter, has emerged to fit that role. And then we're going to talk about the impact on DevOps and security. And then we're going to talk about, like, why isn't everybody doing this already and what's the catch? And then we'll have a little bit of time for Q&A, and feel free to ask anything you'd like along the way. So the original problem, circa mid-70s, you have devices that are now being connected and communicating with each other using this neat little protocol called IP. At the time, there is no net flow controls, there is no traffic direction, there's no switching intelligence. These networks are being built and designed by electrical engineers for the most part, because computer science was still a nascent discipline. It was a sub-discipline of electrical engineering in many cases. And so there was no software running on a switch. You just had what's effectively wires inside a box. And so when a packet was transmitted from one device, it went to all devices. Much like you would see in a unmanaged routed LAN environment today. So that's great. Any device can talk to any other device, and when it transmits, we have a high level of confidence that that message, or that packet for that matter, is going to reach the intended destination. And yeah, there's some collateral damage of like noise that's going to these other systems that we're not actually trying to talk about. But you know, you want to make an omelet, break a few eggs. So every single system on every network has a problem, and that is you're receiving a stream of IP packets and it's not clear which ones are yours. And so everybody had an application running in user land that I'll refer to as the Seagull packet analysis. This thing basically ran constantly and looked at every packet as the NIC received it and determined, is it mine? Is it mine? Is it mine? Is it mine? For every single packet. So since this runs in user land, it competes with resources of other programs that were running, like analysis programs and other communication applications that were being researched and developed at the time. And since it analyzes every packet from the NIC, it had to load the packet from the network interface into memory so that the analysis program, the Seagull packet analysis program, could interrogate it and determine, is the address in this IP header me, or is it not me? So what that means is that the resource consumption scaled linearly with the number of packets received. And as we know, the law of networking, doubling the number of devices would roughly square the aggregate compute required to analyze those packets as transmitted over the network. So that's bad because you hit a ceiling where suddenly the only thing that anybody is trying to do is figure out which packets pertain to them and which packets do not. So this is obviously unsustainable. So this is the old problem. Sorry, is
I think that's just an unmuted. Stand by.
Yep. Awesome. So this obviously isn't sustainable. So we need a solution. What do we need to solve this problem? We need something that allows us to execute a pass-fail on a known or predefined packet relevance rules, most notably the destination address in the header. Does that match a predefined value, most notably the system's own IP address? We need resource consumption that is independent of packet quantity, and we need something that's safe to run, that doesn't compete and collide with other programs' resource utilization and the kernel itself. This is all Unix, by the way. So we enter the Berkeley packet filter. Some extremely smart people at Berkeley and Stanford and some of the other research universities devised this genius methodology for achieving exactly that solution. So there is a concept called a pseudo device or a virtual device that is instantiated by the kernel. It exists outside the scope of the kernel and outside the scope of userland. And it relies on a memcache mapping, which if you don't know what that is, it is a memory segment that is set aside and dedicated and hard affixed to multiple processes. In this case, the network interface that's actually writing data, the packet headers into that memcache, and the BPF pseudo device, which is running outside of the kernel, would also be mapped to that memcache. And since IP headers are a fixed length and predictable, we don't have to do any analysis to figure out where we need to look in those memory blocks in order to do the analysis. So this pseudo device would be instantiated with a set of instructions. This entire concept is written in assembly for extremely high throughput and high performance, and it references a flat registry file that defines the matching criteria. So is this a match, is this not a match? What this functionally yields is a yes, no in approximately 1 CPU cycle per packet. But in many cases, this can be done with co-execution. So it's not in competition necessarily with other execution steps for other programs. And in obviously more modern architectures where we have multiple cores and multiple threads, this can be dedicated to essentially unused execution. So if you think of turning over a CPU, if you don't consume all of the threads for each of the cores, you have essentially wasted resource. So BPF pseudo devices are a great way to sort of saturate that in a non-competitive way. So the Berkeley packet filter was standardized and deployed in every major Unix build since 1986. It was inherited by all Linux builds. So the Linux kernel contains the Berkeley packet filter. And a little bit of trivia, if you've ever made a firewall rule using firewall D on a Debian-based system like Debian or Ubuntu, you are actually under the hood creating a BPF pseudo device with a flat registry file that maps to the rule that you've defined. So if you want to block traffic outbound to a particular IP range, that would be reflected within that flat registry file, and that pseudo device would interrogate each IP as it is being written into the NIC, and it would injunct or intercede in the delivery of those packets as you've defined them. So that is the Berkeley packet filter. Do we have any questions thus far? Awesome. So let's fast forward to like 2010, a cool like 40 years from the original problem. We now have very different problems. And one of those problems is we have compute engines that are extremely high power, very complex, and very hard to interpret or understand. And there's no one individual with sufficient knowledge of what goes on in every part of this kernel, with very few exceptions, who could be able to interpret or interrogate the signal that's coming out of these compute ecosystems, most specifically the Linux kernel. So largely the kernel has become Voodoo. There are tens of thousands of functions in the Linux kernel. Most people never see or interact with any of these. Linux is a beautiful layer cake or parfait, if you will, of lower level and then subsequently higher level and higher level and higher level functions that call each other in a way to produce and express desired behaviors to create and sustain an operating environment for other software. That's what the Linux kernel does. What that means, because you have functions calling other functions and you have services and subservices that are all interdependent upon each other, is you have an extremely high transactional velocity, like many more interactions within the kernel than most people realize is going on. Additionally, kernels are rapidly changing, like daily pull requests and nightly builds, and they're heterogeneous. The way that you interact with a Debian-based kernel is different from how you would interact with a RHEL-based kernel or a CentOS-based kernel. They have different higher order functions, they have different conventions, and so what that means is that if you try and write a solution for one, it doesn't necessarily work with the other. Additionally, there is no good way to look inside the engine while it's running without incurring a massive performance overhead. So instrumenting a kernel is extremely painful from a performance standpoint. You are essentially sticking a looking glass into the middle of an F1 race car engine. Also, authoring the instrumentation for a kernel is extremely expensive. It requires very hard to hire talent, and it introduces a lot of uncertainty, both in performance and stability. See kernel modules instrumenting individual functions with ftrace or kprobes or what have you. So this is a big old problem because, like, lots of people use Linux. If you run containers, almost certainly you're running Linux-based containers. If you use Kubernetes, almost certainly you're running those nodes on Linux-based nodes. You are almost certainly deploying pods that are Linux pods. I know Drew talks about this a lot. Tanzu certainly maintains some of the world's largest Linux ecosystems, or Linux forests. And so because Linux is so broadly used, it has become more and more important for us to get better and better insight into what's actually happening under the hood. But for security and safety reasons, the kernel was not designed to allow that, right? If you have access to the kernel, you have access to genuine secrets like encryption keys that are not supposed to be revealed and all that sort of stuff. And so that poses a problem because we want to look inside, but it's designed in a way that we can't look inside. So how do you solve this problem? Well, and this is a guy named Destin Sandlin. He lives down in Alabama, and he runs a YouTube channel called Smarter Every Day. Episode 259 is fascinating. In this episode, he identifies that he understands what a carburetor does in an internal combustion engine that uses a carburetor. And he understands that there's a choke in the throttle, but he's never seen the inside of one working before. Why? Because like you can't look inside a carburetor. It's a closed system, and you can sort of look at a diagram, but it's actually a fairly beautiful process. And so what this episode of Smarter Every Day is they custom manufactured a clear see-through carburetor, and they, in a very sketchy way, line it up to, I think it's a generator or a lawnmower, and they turn the engine on and they observe what the behavior is with the high-speed camera, and they show the aerosolization of gasoline oil mix, I think it was gas oil mix, as it's being aerated by the carburetor. And this is a great way to think about eBPF. You are essentially creating a magic window into an engine, and you're doing it in a way that is safe and proven. So what do we need to solve this new problem? A way to see when a predefined state occurs at a predefined place within the kernel, resource consumption that's independent of intra-kernel activity, and a solution that is safe to run. This sounds very similar, right? We've seen a problem like this, and we've seen a need for a solution that looks and feels very similar. So some folks over at Netflix and some open source folks about now 11, 12 years ago, maybe even a few years prior, looked into the structure of BPF as an apparatus, and they thought, what if we took BPF, which is a really nifty design to analyze IP packets as they're flowing into a system for dump on the floor or load into memory, so that we can interact with that packet as it's meant to be received. But what if instead of interrogating packets, we interrogated other things like syscalls, function entry exit, other types of network events like socket open, socket close, process creation, session creation. And what if we could do that with all of the benefits of BPF? So the extended Berkeley packet filter is literally just an extension of the BPF functionality to these other intra-kernel communications that historically you would never have had an opportunity to get a live data feed from without compromising the stability or the performance of the system. So when X happens, check if Y is true. If yes, then A. If no, then B. Oops, sorry, I'm skipping slides because the magic mouse is terrible for navigating slides. That is exactly the same format of analysis that is used in a BPF pseudo device. It's just analyzing an IP packet. There's near zero compute memory overhead. We are many generations of processor down the road. And as I mentioned, we now have multi-threading, we have multiple cores. And so there's almost always underutilized execution paths on the processor that we can take advantage of to essentially nestle in this type of it's not sidecar execution, but executions that are not the primary functional application. Now, one of the biggest pieces of eBPF that I think makes it really relevant in a modern sense is it is JIT compiled. And what that means is that the eBPF module that exists within the Linux kernel will compile a bespoke BPF virtual device instruction set in assembly at runtime. So when you go to initiate an eBPF program, you are asking the kernel to create a pseudo device. You don't actually tell it the assembly code that's been sort of abstracted away with the BPF library, but it's JIT compiled, so it's much easier to maintain than kernel modules. It also can be performed after init, so you don't have to restart a system in order to get that visibility. And if anything happens to compromise that instrumentation, you don't have to restart the operating environment in order to reinitialize that visibility the way that you do with kernel modules. So many EDR solutions out there have fantastic Windows solutions and a very small number of kernel modules that pertain to very out-of-date Linux builds of various flavors. And in one case, the most up-to-date version of, I think, Ubuntu that you could use for one particular market-leading EDR solution was over 6 months old, which is frustrating for developers. They want to be running on latest. They want to be taking advantage of the newest features that are being released for the Linux builds that they are using to build their software on top of. And so it's frustrating when a security or an observability solution is restraining which version you can use. And then finally, it runs outside of both kernel and user land. And this is great for security. That pseudo device is unassailable by users. You have to ask the kernel to create it, and eBPF is written in a way that it is extremely difficult for anything ever to directly interact with or compromise the execution of that pseudo device. Certainly from user land with sufficient privileges, you can generate an instruction to the kernel to eliminate a pseudo device. But that in and of itself is a command execution. And so that will be seen by the pseudo device before that command is actually executed, because the request happens before the completion of the request. And so you will be able to see exactly who and what requested that termination of that pseudo device. So application developers were really the earliest adopters of eBPF. It was largely platform development teams at Netflix. They were dealing with issues of scale that nobody had ever seen before. They were pushing the boundaries of cloud technology in ways that nobody had ever pushed it before. This is the per user playout device orchestration ecosystem, and refining and tuning of their machine learning algorithms to drive efficiencies within their media catalog and what gets presented to which user based off of what they've watched and what they've rated and all that sort of stuff. So they were dealing with very complicated infrastructure problems, and lo and behold, there was no real good way to see what the heck was going on in a kernel. So when something throws an error and there's no sufficient error messages, what do? You try and figure out how to get lower. Well, what do you do when you're at the lowest level? You look into new technologies or build a way to see deeper into the kernel. Now, security and observability solution providers are getting deep into eBPF. Elastic is one of them. There are certainly others, and all the formerly associated eBPF solutions are in fact listed on the website. But a good open source eBPF project is OS Query, which is a tool that you can use to essentially ask questions of a system. What are all the running processes? What is the current user configuration? Show me all of the administrative accounts that currently exist within this operating environment. So OS Query used to run as a userland program. It was very snapshotty. So you would give it jobs and it would perform that job at a tempo. That's obviously not great from a security standpoint. And it can be sort of hit or miss from an observability standpoint. So they adopted eBPF, and now it can sort of just run passively all the time and provide a data feed out, and you can sort of tap into that whenever you want, and it's significantly more convenient. It also happens to consume about 20% less CPU overhead. So that's pretty awesome. So what does this mean for DevOps? And sorry for the creepy picture. This is from Gremlins, the 90s movie that haunted my dreams for years and years as a kid growing up. What is a gremlin? A gremlin is a type of bug that is ephemeral, fleeting, conditional, hard to reproduce. I would guarantee everybody here has dealt with a gremlin bug before. Builds failing, sometimes under question mark conditions. And oftentimes these gremlin bugs are the hardest to track down, the most expensive to to perform root cause analysis on, and they cause the most customer frustration. They cause the most internal partner frustration. If you provide a platform for somebody else and that platform fails intermittently, maybe once a week, maybe once a month, but it fails in a glorious or terrible way, that's not a good thing. And if you can't figure out why it's doing that, that's very frustrating. So by leveling up the general observability across the board for any application that's running in Linux and the Linux kernel itself, you can observe what is taking place adjacent to the actual command executions, and you can literally observe the error message being floated up the stack. That's a really powerful piece of information to have, because you can essentially wind back the hands of time and look at specifically what was the context immediately before this error threw. Is it a floating point? Is it an issue with floating point? Because that's literal Voodoo. Is it an issue where we are trying to co-execute, or is there a cache conflict, or am I trying to invoke overlapping similarly named packages in a Linux environment, and we have like a routing conflict or a permissions conflict that only appears when we try and do these two things side by side? It is horrifying to me how often this is the case. So identifying gremlin bugs by just getting better visibility across the board. Second, when it comes time to point fingers, when we're in crisis mode, the less ambiguity there is as to what took place and what is the current state, the less room there is for the blame game. So what I mean by that is, if you know exactly what happened and you have a dash cam running in your car and somebody runs a red light and T-bones you and you have video evidence, it is extremely difficult for that person to argue that reality didn't happen. If nobody has a dash cam and there are no witnesses, it is very easy for finger pointing to occur. So from a collaboration and working together and cohesion standpoint, eBPF actually brings a level of granularity to the observability plane that allows for much more objective crisis time resolution. Sev1s are no longer war rooms. It's like a response effort. And when things are broken, when something fails, when someone's code throws an error, it is painstakingly obvious who the culprit was. And there's no arguing for 9 months that, no, it's not me, no, it's not me, no, it's not me. This also helps in multi-vendor resolution, because we've all been in the position where you're working on something that involves 3 different vendors, and it is not crystal clear from the error messages that you are receiving what is taking place under the hood and which systems configuration or misconfiguration is causing the problem. And vendor support teams absolutely love to punt. I know I used to work for a system integrator, and one of the value propositions that we would go to our customers with is, you don't need to know as much as my most experienced team members know to get all of the vendors in line and stop the bickering. So this is a huge benefit, because in crisis time, it's nice to have the dash cam. And finally, instrumenting your own build environments. So this is a DevOps meetup. So we all care about build ecosystems and build pipelines. And who here hasn't run a build pipeline unchanged, maybe multiple times a day for like 2 months, and then all of a sudden it breaks and it doesn't work? And you look at it and you scratch your head and you say, there have been no code changes. This environment has not been modified. There are available resources. Am I going insane? And so build environments are some of the most complex ecosystems where those sorts of gremlin bugs can pop up. And it is notoriously difficult for DevOps teams to root out why a particular build failed in a particular, at a particular time. And being able to provide that feedback and discerning between a failure in the build because of application code issues or build instruction issues as opposed to build environment issues. And that sort of gets back to the blame game message, but really just discerning the ridiculousness of what feels like, arbitrarily failing builds is really nice. This is also super important because everybody here should theoretically be familiar with the SolarWinds attack. There was a startup camera company, like security camera company, that was attacked. I believe that was like early 2021. They had a compromised Jenkins environment. Vercator, I think, was the name of it. Yeah, the CISO for that company started 4 days before that breach went public. And I spoke to him about 2 months later, and he seems to have been through it. But yeah, securing your build environments is super important, seeing exactly what's being executed. In the case of SolarWinds, there was a 9 to 12 month dwell time where the attackers actually wrote a bespoke program that would take an inbound package that was being cloned from a code repository, inject malicious code into it that would build a backdoor into the Orion management package that was being built. And with eBPF, you can literally see this happening at the file system level. You can see it happening as those random additional executions are occurring that don't seem to correspond with the rest of the build pipeline. And you can see it when you run that compromised package, because it's going to try and open up an outbound secure connection to some C2 service. And so in every case, that sort of compromise, which historically is impossible to protect against and hair-tearingly frustrating to sort of resolve, if you can secure your build environment better, then you can stop all of the sort of public headache that occurs. But if you run eBPF on all of the operating environments where you're also running software that's coming from a supply chain, so vendor provided software, open source software that you're acquiring and not doing a line by line code review on, you can actually see what its behavior is at runtime. So what does this mean for security? Comprehensive, clear visibility into what the attacker did. Unobfuscated. And this is probably the most important piece of eBPF in security. This is honestly what was most interesting to my customers when I was with CMD, that company out of Vancouver, was because eBPF looks at the data stream from the perspective of inside the kernel, and the kernel needs things to look a certain way in order to handle it properly. Obfuscation techniques don't work. If you're not familiar with obfuscation, obfuscation is a set of techniques or a methodology of making an attack unintelligible. So that could be using a tool like Bash Obfuscator. So if an attack is taking place via, say, a reverse shell, and the attacker is concerned that that reverse shell may be identified and all of the transactions may be observed. Well, if you're observing from user land and it looks like a million characters of nonsense, that's really hard for a security analyst to figure out what the heck the attacker was trying to do. But all of that nonsense interpreted by Bash is handed off to the kernel as a very simple, write this file or read this file or do this thing. And eBPF sees from the perspective of inside the doorstep of the kernel at command execution for command execution eBPF use cases. And so what that means is you don't have to do any interpretation or de-obfuscation. You can literally just watch what the program is doing exactly as the kernel sees it. And you can't lie to the kernel because the kernel is the thing that does all the work on the system. Additionally, it retains the fidelity of time series. So another sort of, I would say, adjacent form of obfuscation is time obfuscation. One of the things that we see in intentional and manually operated advanced persistent threat type attacks is out of order essentially creating an out of order sequencing in any sort of telemetry. You can do this in a bunch of ways by creating delays or bundling processes in a certain way that they are prevented from writing to syslog until some certain point within their execution. And you can sort of use techniques like that so that it's not do this, do this first, then this, then this, then this, then this last. When somebody actually finds what you're doing and looks at the logs or looks at syslog output, something along those lines, it would look completely out of order, and it makes it significantly more difficult to figure out what was actually happening. But again, you can't lie to the kernel. You need the kernel to do the things in a specific order in order for those attacks or those execution sequences to achieve the attacker's desired behavior. And so you just watch from the perspective of the kernel. And so there's really very little interpretation. You could literally see exactly what happened. When, where, by whom, so which user executed it. You can't obfuscate or you can't cover your tracks by doing shell hopping, which would be like a shell generating another shell, creating a process that creates a child process that then terminates the parent process and the originating shell. So you just have this child process that's floating with seemingly no parentage. Well, all of that parentage exists. It just is very obviously transparent in the context of the data stream that's available within the kernel. So you can just watch exactly the pathway and terminate in a multitude of ways, react from a security standpoint. This creates opportunities for new policy engines that operate with enough clarity to actually sieve out bad behavior from the good. The biggest problem with security tooling today, traditional security tooling today, is whenever you put a block rule, whenever you try and prevent something from happening because bad actors do that thing, they're doing that thing because they know that legitimate users also do something that looks very similar or is exactly that thing. And usually legitimate users are doing it to try and generate value for their organizations. So when you block that from happening, you are effectively reducing the efficacy of that compute resource and the person that's actually trying to use that compute resource. So eBPF provides a level of detail and granularity and visibility to create layered policies that say if X and Y and Z are all in co-occurrence, we know that's bad. So don't let that happen. But if X and Z are occurring at the same time, that's fine. And you can create very nuanced policies that allow for the good behavior and block the bad behavior. It is significantly lighter weight than any EDR solution in the marketplace by oftentimes an order or multiple orders of magnitude. When we used to run tests, it would not be uncommon for a traditional EDR solution to consume between 15 and 20% of the available CPU cycles when full essentially audit D is turned on. And that data feed is being provided into the EDR agent. And CMD's eBPF solution was like 0.01% of CPU utilization. So that was always nice to discuss sort of how much less of a cloud spend there would be, especially in horizontally auto-scaling applications. Finally, it can be implemented as a daemon set service on Kubernetes. So if you're not familiar with daemon sets, it is essentially a subclass of service definition, and it inherently means one of a pod for this service per node, or the number of pods that you specify in the daemon set configuration per node. And since eBPF is looking at the underlying running kernel at a low enough level, you can actually watch all of the pods in the Kubernetes environment and the kubeadm process itself and the underlying operating environment that the kubeadm application is running on, and protect the entire stack or provide observability on the entire stack. And nobody knows. Nobody else knows, right? So your application teams don't have to instrument agents within their containers. you get full resolution. There are multiple services out there that have overcome sort of the Kubernetes triangulation to figure out which container, which pod ID, which namespace, which node a particular thing is running in, and providing that relevant data back so that a responder from a SOC or a NOC can very quickly go to where the problem is. Leveling up telemetry across network processes and file transactions provides a 360-degree view of an asset. We generally don't get that level of clarity. And finally, it's not a bastion solution. You're not jumping into a host that's going to track all of the things that an internal actor is doing by way of jumping to the actual host that you want to get to. There are a number of solutions out there that provide bastion-based solutions. There are certainly reasons to use bastions in production environments, like not having to manage keys or authentication for low-level access like SSH into production hosts. But there's a limitation to bastion. You're only watching the activity on the bastion host. So if somebody manages to pop a web application that's running on a Linux host or in a Linux container in your environment, and they are able to produce a reverse shell, the bastion host has absolutely zero visibility into it. So that's what this means for security. So what's the catch? This sounds amazing. I have painted an amazing picture of eBPF. So why is the world not all, like, why are we not, living and breathing eBPF every day? Well, it's hard. It's really hard. eBPF has a verifier, which you can think of as a gatekeeper that imposes limits on what can and cannot be instantiated by the kernel as an eBPF pseudo device. Things like limitations on number of instructions up until kernel 5.5, I believe. You could run up to 1 million assembly instructions, which is surprisingly not very many when you are unable to leverage unbound or while loops. Anybody who's written code that interacts with an operating environment probably has wanted to use a while loop type logic set. You cannot use that in eBPF because you can create essentially an echo chamber or a feedback loop within the kernel that causes that essentially will compromise the kernel. And so the only role of the eBPF verifier is to stop patterns that we know are unsafe for the kernel to run. So what people do is they create fleets of eBPF pseudo devices that each do different things. Lo and behold, it sort of looks like a microservice architectured application. And there is some discrete handling per major kernel family. So the way that you actually execute the eBPF pseudo device may vary slightly. And so there is still some per Linux flavor build and design, certainly in the userland code that is meant to extract the data and send it out somewhere, presumably, because this data is not useful if nobody's looking at it or nothing is analyzing it. So we generally want to send it out to some listening service. And so that code may need to be authored on a per flavor basis. That is certainly easier than kernel module development, but still represents a substantial amount of work. And nobody teaches this. There are no college courses today that teach eBPF that I've been able to find. I haven't looked in a couple of months, but eBPF is a very nascent ecosystem. It is growing extremely rapidly. I will tell you, in the next 2 to 3 years, there will be novel solution concepts that are born out of the capabilities of eBPF that could never have existed prior to. But the problem is, it's really hard to find people that have the skill set or have any prior eBPF experience, and there's very little, the community is still relatively small. In the case of commercial solution solution developers or solution providers, much of their eBPF development is closed source. So it still is somewhat hostile. There is an open community or a community of open source developers and researchers that are using eBPF to do new and different things that are very collaborative and very open, and there are open communities for it. There's also an annual conference, but it's hard to get templates for how to do something. And so that makes it difficult for companies that are trying to accelerate their go-to-market delivery on these types of solutions. It makes it hard if you run into a problem, if you have a project with eBPF. It's really like a space that is largely undefined. Personally, I think that sounds awesome because if you're into exploring that space, you can very vastly increase the value of your skill set to a wide variety of companies, both observability and security, possibly more into the future. And lastly, eBPF wasn't introduced into the Linux kernel until mid 2019. So legacy Linux environments aren't necessarily compatible. That makes it difficult to sell into a lot of enterprise spaces where there are things like CentOS 5 hosts running, which is like, ugh, from a security standpoint, that just like gives me the jimmies. All right, so that's all the stuff. Are there questions?
I've got one.
Shoot.
How do I get started? Like, I was looking around like eBPF getting started or like learning, and I see, look at that. So like,
so some of these are describers. This is a paper on eBPF. This is somewhat outdated, but eBPF.io, the actual project website, has lists of projects. So the project landscape. And some of these are open source. You can literally just jump in. Kubectl Trace is an open source project. You can read their source code. You can interrogate it. There is a Slack channel for the eBPF project, and you can read all the pull requests against the eBPF core code base. There are also conferences, and so Cloud Native, eBPF Summit, etc. So lots of resources. This is and conference coming up September 28th, 29th. But yeah, this is a largely open source ecosystem, very much largely open source. And that's super awesome because it creates learning opportunities. If you wanted to just start playing around with it, there are tutorials out there. I didn't include any of these in my prezo, but I can probably scrounge a couple of them up for like, recent like Linux builds and relevant tooling that you might use. And, we can include those in the follow-up email.
Cool. Yeah. So it's like a first touch is like pick any of these things on the project landscape page and just like pick what calls out to you and play around with it. But and then like to get serious about it, it looks like kernel development. Is that what it looks and feels like if you actually start contributing?
So yeah, so this is part of the reason why it's really hard to hire for the skill set, is because you need a sufficient understanding of the use case space. So you need to find people, like the people that did much of the work for CMD, which was one of the best engineering teams I've ever worked with. And super happy that the overwhelming majority of them moved to Elastic, brought their knowledge and continue to contribute there. But many of them had very low level coding, kernel or sort of bespoke hardware. So people who've done FPGA development, it's a lot of that sort of logic. But you also need to have an understanding of the security space and what a security analyst needs, or what a digital forensics incident responder would need as a data output, so that you can build your pseudo device instruction set and your registries in such a way that you ultimately yield the picture that's useful to the end consumer, the end user. And that's a rare, I don't want to say a rare collision of skills, but it's a relatively uncommon collision of skills. And most of the people that have that skill set today are oftentimes you face a lot of hiring inertia. They're well paid in the positions they're in, and they're typically very well taken care of in their position. So if you want to become one of those people, learn eBPF and learn how to interact with the kernel and various handles. I had never looked at the Linux kernel before I went to go work for CMD. And it is astounding how deep it is. You can get lost in like 100,000 rabbit holes if you really go exploring what a particular function is in the Linux kernel and GNU and so on and so forth. One piece that I didn't mention is CMD went to market as a security solution. So we would talk to SOC analysts and SOC managers, to incident responders, to DevSecOps folks. But we always ended up speaking to the DevOps team or the operations observability monitoring team, because the data stream that we were able to produce, just in terms of command execution, we weren't looking at metrics. We didn't look at anything network related. It was literally just what commands are being executed by whom at what point in the Linux environment. And a great story. There's a company, I believe they're headquartered out of London, and their like market offering is basically like anti-plagiarism. So people submit papers over a web portal, and they use like a bunch of really advanced like text analytics to determine if somebody is likely to have plagiarized somebody else for, you know, with a paper that has previously been submitted. So love them or hate them, that was the company that I was doing a POC with. You probably know the name of it. But the heavy Kubernetes shop, we deployed our eBPF agent into a 40 node Kubernetes cluster that was their dev environment. And we were generating somewhere in the neighborhood of 3.5 million command executions an hour, which is a lot of command executions. It put a lot of strain on our backend. We were at the time a roughly 45, 50 person startup using a MySQL cluster backend, which was not sufficient at the time. So fortunately, we have access to a better backend. But one of the amazing things was we did some sort of post analysis. So we let that run for a couple of days, and we did a meeting with them. We walked through the data that we saw. And one of the things that we asked them, we were like, there was a lot of SED, like 3 out of every 4 commands that are being executed in your environment are SED commands. And SED is like reading and writing files in place. That's what it is, right? If you're not a Linux person. That's very weird, because SED is sort of considered unsafe. It's very unbounded. You can break lots of things with SED. It's also directly interacting with the file system. And since it's a Kubernetes environment, it's sort of like, why are you doing this so much? And it turns out that they were using a message queuing service, and the replacement effect of flipping the read unread bit in that message queue was SED. They would literally SED the bit. And so what's insane to me is that nobody in the entire organization's development team or DevOps team had any awareness that this was the behavior of that message queuing service under the hood. And once we sort of identified that, we were able to back our way into it. We were able to look at command execution streams and build a pattern, and then find where that was happening and look at sort of parent lineage of process execution. And we're like, yeah, it's this message queuing service, which like I wasn't familiar with. And they were like, oh, that's super interesting. We had absolutely no idea. But imagine if it's not SED, imagine if it's something like, oh, say Log4j that's running at the very low level on your system and you don't know it. And it's really hard to find because it's deeply nested within dependencies that are never explicitly called within any of the code that you download. That's the sort of thing where it's very valuable to get this deep level of telemetry and insight into what's actually happening. And so I love telling that story, because most people run Kubernetes and run packages, use baseline containers to build on top of, and you're doing this like really incredible stuff. And it's like, you have no idea the mountainous shoulders of geniuses that you happen to be standing on in order to be able to extend your application code in the way that you are. And so I got a profound appreciation for that by looking at these ridiculously large data sets. And obviously you don't need to interact with the whole data set. A lot of what we talk about in terms of deploying this from an Elastic standpoint is, how do we pare down this information to the useful stuff? Or how do we identify where it's identical but another instance of with a different timestamp, and how can we store that and represent it in a way that's meaningful to humans so that it's not, an avalanche of information coming at you out of what is effectively an F1 race car engine, but ultimately making it more useful.
That's a cool story. Thanks for that. 3 out of every 4. That's a special circumstance.
It was very head scratching because I have only ever broken things when using SED. So
raised a few eyebrows.
Yeah, I was like, I've seen that. I've used that program before to break things. That's a lot of that program.
That's frightening.
All right. Any other questions? I know that was a lot and I talk really fast, so don't feel bad. Oh, we have like 7 things in chat. The resources link. Yes. Here are the resources link. I will actually let me exit this presenter mode. How can I get out of this presenter mode? Use a slideshow, and let me just do this and copy and paste. Here we go. I think that worked. I'm missing an F on the last link. That was hasty. Better.
There we go.
Yeah, so these are all good resources. Some of them are sort of talking about what is eBPF. A couple of these are, as you can see, YouTube videos. I think both of these are talks by the same gentleman from YouTube. I think it's like Nathan Brennan or something. Yeah, so Drew will be sending out a recording at some point with a follow-up email. And as I understand it, this will eventually make its way to YouTube. So hopefully when family members ask what I do for a living, I can just send them this link and say, here, watch this for like an hour and your eyes will glaze over.
Then when you wake up in 2 hours.
Yeah.
No, this is really cool. I had no idea, like the back of my mind knew what BPF was, but was not aware that the concept had been extended into this area. That's really cool.
It's like a footnote during one day of like OS class in college if you're like a comp sci major. And so it's like BPF, that is an acronym that I've heard of. I don't remember what it is. That's like most people's entire experience with it. But the cool thing is it's been around in Unix kernels, and so all Linux kernels since the year I was born. So it's like 36 years of stability. We know it works. It's very powerful. So extending it made a lot of sense. I love the story around sort of this need to discover a better way to garner insight. But
I like it. Yeah, and I like that the word Berkeley showing up in something related to the kernel tells you that like it has to be good and it must be at least 3 or 4 decades old.
Yeah. All right.
Cool. Any other questions or comments from the crowd? Okay. And thank you so much, Thaddeus.
Yeah, thanks for having me. And if anybody has questions about Elastic, security, observability, enterprise search, feel free to hit me up. My email will be in the follow-up note that Drew sends out. And yeah, thanks for joining today.